In section 7 of chapter 11, we're going to be taking an old concept that you learned way back in the day, back in, I want to say like 6th grade maybe, and we're going to be applying it to this trigonometric chapter involving the unit circle and trigonometric functions. This is what we know thus far. We know these 6 trigonometric functions and how they can be reread. Sine and cosine are just sine and cosine. Tangent is sine over cosine. Secant is 1 over cosine. Cosecant is 1 over sine. Cotangent can be written as either 1 over tangent or cosine over sine. That's old school. If you remember back in the day, when you first started learning about right triangles, you might recall that there was a specific formula that we had you all memorize because it's a formula that applies for all right triangles. The formula I am alluding to is the Pythagorean theorem. That is to say that a squared plus b squared is equal to c squared. If you take 2 legs of a right triangle, measurements a and b, you square them and then add their squares together, you would get the value of the hypotenuse, c squared. That's what that talks about. This formula works for all right triangles. Seeing as how we're dealing with unit circles, which have in them unit triangles, which I have on the screen right now, if the Pythagorean theorem works for all right triangles, and unit triangles are themselves all right triangles, then it would make sense that there is a Pythagorean version of that formula for unit triangles, except we are going to be changing A, B, and C. Because A can represent a side length of a right triangle, B can represent the side length of a right triangle, and C is the hypotenuse of a right triangle. But for our unit triangle, we recognize that cosine is the x value. It is the length of the triangle, because cosine is adjacent over hypotenuse, but the hypotenuse measures 1, so it's just the adjacent leg. And then sine is the y value. It's the opposite side, because sine of the unit triangle is opposite over hypotenuse, but the opposite side is the only thing that's going to contribute to that equation. Therefore, we could rewrite that Pythagorean theorem as what is called the Pythagorean identity for trigonometry. Sine squared of theta plus cosine squared of theta is equal to the hypotenuse squared. Well, 1 squared is just 1. This is the Pythagorean identity for trigonometry. Just like how the Pythagorean theorem is true for all right triangles, the Pythagorean identity is true for all unit triangles. There is a slight issue. The Pythagorean identity is really nice because it's going to help us manipulate any kind of expression or equation that has either sine or cosine in it to the second power. It's going to help us manipulate that, and I'll show you how in a little bit. However, sine and cosine are not the only functions that we have. Now, it's true we can manipulate tangent, secant, cosecant, and cotangent into sines and cosines, but it's kind of a major step to take when we're already going to go through a really complex simplification process as it is. I'm going to show you that there's actually 2 other variants to the Pythagorean identity. I am going to show you where they come from, because I will be blunt and honest with you. These other 2 identities, which are also formulas like sine squared plus cosine squared equals 1, I, as your math teacher, I don't have them memorized. I don't know them. If you were to ask me what they are off the top of my head, I would not be able to tell you. The reason why is because they are ridiculously easy to find. All you do is you start with the original Pythagorean identity, sine squared plus cosine squared equals 1. And then, in my first iteration, what I'm going to do is, if I want to have a Pythagorean identity with, I don't know, let's say secant in it. Secant is when I have 1 over cosine. So if I want secant to show up, I'm going to have to divide the 1 by cosine squared. But I can't just divide the 1 by cosine squared. I've got to divide everything by cosine squared. If you divide everything by cosine squared, you're going to get a variation of the Pythagorean identity that's going to involve different trig functions. You are going to get sine squared over cosine squared is the definition of tangent squared. And then you're going to get cosine squared divided by cosine squared. That's just equal to 1. And then we're going to get 1 divided by cosine squared. 1 divided by cosine squared is secant squared. And this is another Pythagorean identity. All I had to do is start with the original one, sine squared plus cosine squared equals 1, and just divide everything by cosine squared. As soon as I do that, I get a different version of the Pythagorean identity. This one is going to help me solve or simplify any expression that has tangent to the second power or secant to the second power in it. And then you can probably figure out what I'm going to do in the problem number 2. Problem number 2, I am going to divide everything by sine squared. Because if I divide everything by sine squared, then I'm going to get another variant that's going to encompass the last 2 trig functions we haven't talked about yet. Sine squared over sine squared is equal to 1. Cosine squared over sine squared is equal to cotangent squared. And then lastly, 1 over sine squared is equal to cosecant squared. And then this is our last iteration of the Pythagorean identity. And now we have 3 Pythagorean identities, each of which deals with the trig functions in all 6 categories. Now I do also want to mention, if you want to be super technical, there are more variations to this, but they're just algebraic. Another identity, let's just deal with the first one, is if I just subtract 1 from both sides, this is the same thing as saying tangent squared of theta is equal to secant squared of theta minus 1. Which is the same thing if I just subtract the secant squared to the other side, is the same thing as saying tangent squared of theta minus secant squared of theta is equal to negative 1. These are all 3 different variants of that trig identity. Depending on the problem, one variant might be more useful than the other. So I have 4 problems up on the screen right now. I am going to simplify these. Now you might look at that, at each one of those, except for maybe number 4, and go, those look relatively nice. They don't look like anything crazy is going on. However, after I pass them through the Pythagorean identity, you will find that each one of these, for the most part, can be rewritten in a much, much more simplified manner. Now, problem number 1, as a mathematician, screams at me to use the Pythagorean identity. For all of you who are relatively new to this, it might not be screaming at your face as much. Here is why I know that we're dealing with the Pythagorean identity. It's because the Pythagorean identity is largely used whenever you have a trig function to the second power combined together with a 1, either through addition or subtraction. Because if I deal with the fundamental Pythagorean identity, sine squared plus cosine squared is equal to 1, I could rewrite that by subtracting cosine squared from both sides and find that sine squared is equal to 1 minus cosine squared. What that means is anytime I have a 1 minus cosine squared, a binomial, I could replace that with sine squared because they're equal. In this problem, I have a 1 minus cosine squared, so I can replace it with sine squared. So this problem is going to turn into sine squared of theta divided by sine squared of theta. And what do you know? I have sine squared divided by sine squared. That's just equal to 1. That means this problem, as nice as it probably looked initially, could be simplified into a 1. This is a fancy way of writing the number 1. In problem 2, I have a binomial, cosine plus tangent squared cosine. They both have a cosine in common. Therefore, I could factor out a cosine and be left with 1 plus tangent squared of theta. 1 plus tangent squared of theta is an identity. 1 plus tangent squared, or tangent squared plus 1, is equal to secant squared. And secant is defined as being 1 over cosine. So secant squared is 2 of those. 1 over cosine times 1 over cosine. Whenever you multiply cosine by a secant, they cancel. But I got 2 of them. So this cosine is going to cancel with one of the 2 of them, leaving us with 1 left. Our answer is secant of theta. Now what we also could have done, if we so chose, is we could have taken the route that we did previously, which is to turn everything into sines and cosines. I'm going to show you I get the same answer. This could have also been cosine of theta plus tangent squared is just sine squared of theta over cosine squared of theta times cosine of theta over 1. This cosine would eliminate with the second power, leaving you with cosine of theta plus sine squared of theta over cosine of theta. In order to combine those 2 together, you'd have to have the same denominator. So I'd multiply the first one by cosine over cosine. That would give me cosine squared of theta over cosine of theta plus sine squared of theta over cosine of theta, which is then equal to cosine squared of theta plus sine squared of theta all over cosine of theta. Cosine squared plus sine squared is an identity. That's equal to 1. 1 over cosine, which by the way is equal to secant. I got the same answer. I just did a different tactic. The nice thing about trig identities is do whichever one you think works. They will all lead to the same answer. All right, problem number 3. Problem number 3 is, spoiler alert, I told you it wouldn't go away, factoring. 5 cotangent squared theta plus 10 cotangent of theta plus 5. That's a quadratic. Here, let me replace the cotangents with x's, and this would be 5x squared plus 10x plus 5. All y'all will be able to recognize that as something you could factor. Because I start throwing trig functions in, for some reason, Algebra 2 students tend to have a difficult time recognizing that the algebra you learn, specifically factoring, still applies. I just replaced the cotangents with x's. But I'm not going to cheat. I'm actually going to factor, keeping it in this trigonometric form. First thing I notice, I have a trinomial. 5 cotangent squared, 10 cotangent, 5. All 3 of these terms are divisible by 5. So the first thing I'm going to do is factor out a 5. That'll be 5 times the quantity of cotangent squared theta plus 2 cotangent theta plus 1. Use whatever factoring technique you want. You can use the area model, diamond method, tick-tock method, quadratic formula, completing the square, whatever floats your boat. They will all work. Just pick your poison. But once you factor that, it will turn into 5 times the quantity of cotangent of theta plus 1 times cotangent of theta plus 1. You have the same binomial multiplied by itself, so this is equal to 5 times the quantity of cotangent of theta plus 1 quantity squared. This is the last thing and the reason why I want to do this problem. I cannot apply a Pythagorean identity to this. This is cotangent of theta plus 1 quantity squared. That's not a Pythagorean identity. The Pythagorean identity is cotangent squared plus 1. You cannot apply the identity to that because you're squaring the entire binomial. And you do not distribute the second power to both of these. If I wanted to square this, I would get back to this step. Therefore, this is our answer. There is no Pythagorean identity to use in this. This was basically just a quadratic function, a factoring problem, with just some trigs sprinkled on top for flavor. It's important to know when and when not to apply the identities. Problem number 4 is not going to show up anywhere other than this lesson. It is a little bit of a doozy. I think we can handle it. First thing I notice is I have a 1 plus cotangent squared in the bottom of my very, very first term. I recognize that that is equal to cosecant squared. So I just turned that binomial into a monomial. Then I have a tangent squared, so times tangent squared. I could turn that into a binomial, but I don't know why that would be useful. Plus sine of theta over secant of theta tangent of theta. I do not see any more Pythagorean identities I can use, so now the only other techniques we have is to turn everything into sine and cosine and hope stuff cancels out. So that's going to turn into cosine of theta over 1 over sine squared of theta times sine squared of theta over cosine squared of theta. Then that second fraction that I'm adding is going to be sine of theta over 1 over cosine of theta times sine over cosine of theta. I don't like that I have so many fractions inside a fraction, so I'm going to just turn them into their multiplication of the reciprocal. So the first fraction, instead of being cosine of theta divided by 1 over sine squared of theta, it's going to be times the reciprocal, which is sine squared of theta over 1. Times sine squared of theta over cosine squared of theta plus sine of theta times the reciprocal of both of those fractions on the bottom, which is cosine of theta over 1 and cosine of theta over sine of theta. We have to condense the left fractions and the right fractions before we can handle the addition. This is over 1, this is over 1. You can cancel things that are the same on top and bottom. I have a cosine on top, I have 2 of them on bottom, so one of them goes away. These two sines, the sine squared and the sine squared, give me sine to the 4th power over cosine of theta plus the second set. I have a sine on top and I have a sine on bottom, so that is just equal to cosine squared of theta. Sine to the 4th divided by cosine of theta, you could write that as sine to the 3rd times sine over cosine. So that is tangent of theta times sine to the 3rd power of theta plus cosine squared of theta. I don't see any other identities I can use. I don't see anything else that can cancel out. So that is my answer.